discuss about something called SET Mram.
Back sir.
And SOT. STT, Mram and SOT. STT stands for spin transfer torque. How are we using this spin transfer torque for magnetic random access memory, which has two functions. First of all, it can read and write, and it has a non-volatile memory. These are the functions. Non-volatile, if you plug off, the memory stays there. So first you will understand what is a spin transfer torque. I think we have the basic idea of a spin transfer torque is any electron or any current which mainly involves electrons, the spins are random. We are not in any particular direction. Random spins or unpolarized spin. When they enter a system which has a preferential spin direction, they come out as polarized. That is, having the spins in any particular direction. It's called spin polarized current. Okay. What is this material which has got spin in any preferential direction? This type of material, this is a ferromagnetic. It is Fm. Now, to work it as a read-write device and a memory device, we need to create something called an MTJ. MTJ stands for magnetic tunneling junction. इसका मतलब है you have to create an insulator here and then another ferromagnetic layer. This is ferromagnetic 1. This is now, what is the difference between FM1 and FM2? FM1 is called a pinned ferromagnetic, or where the magnetization is fixed, pinned, fixed layer. And this is a free layer. The magnetization is free, it can change. So it is, मैं इसको dot से join करूँगा. Maybe it is in this direction. But it can change. It can change to this, it can change to that. It is free. So इसको बनाते हैं COFEB से इसको भी बनाते हैं COD से. Both of them are ferromagnets. So can you tell me how we are using the same material and we are creating a ferromagnet which has got a pinned or a fixed direction of magnetization, or one which has got a free direction magnetization? Which factor determines whether it will be free and pinned? Thickness. Basically the thickness. Thickness अगर ज़्यादा होगा तो it will lead to free layer. But if the thickness is low, it is possibly the degree of freedom decreases. It is more likely to be a pinned layer. तो दोनों में थिकनेस का फर्क है. ठीक है. अच्छा, now when I say read and write, basically I'm referring to the bits. Computer reads and writes through bits 0 and 1. It can be 0 and it can be 1. Based upon these two orientation, it will read and write. So when I say 0, it usually means that there is a low resistance to SPC. And when I say 1, it means there is high resistance to SPC. एक लो है तो 0 होगा, एक हाई है तो 1 होगा. Now this resistance is again TMR, and it is equal to maximum लोगों ने इसको बदल देखा है. Okay, what is RAP? Both of them are resistances. Parallel is when the magnetizations are in parallel directions. If they are in the parallel direction, ऐसे होगा magnetization in this direction. It represents RT. The magnetic lines of force are in opposite directions, so it represents RT. ठीक है. What is P? Number in up direction minus number in down direction divided by electrons in up direction plus number of electrons in down direction. This is the polarization. So when this current it reaches the free magnetic layer, यहाँ पे एक टॉर्क जनरेट होता है. टॉर्क कैसे जनरेट हो रहा है? You take this axis से, और ये फ्री मैग्नेटिक लेयर का मैग्नेटाइजेशन डायरेक्शन अगर मान लो ऐसे है, इट इज इन दिस डायरेक्शन. तो फ्री वाला है ये, और मैंने जो इसके जो करंट आ रहा है उसका डायरेक्शन इससे इन दिस डायरेक्शन. All the currents are in this direction. So when they will interact, there will be equal and opposite force. ऐसे होगा. This is the torque. है ना? Equal and opposite force. ये इसको अलाइन करने की कोशिश करेगा, इसको अलाइन करने की कोशिश. So there is a torque arising here. तो मान लो ये अगर सारे इस डायरेक्शन पे होते, इफ दिस डायरेक्शंस वर लाइक दिस, मान लो ये जो बाउंडेड मैग्नेटिक फील्ड की मैं बात कर रहा हूँ, मैग्नेटाइजेशन की बात कर रहा हूँ, ये मान लो दिस इन दिस डायरेक्शन, ये ठीक. तो फिर क्या होता, सारे जो मेरे मैग्नेटाइजेशन spin polarization would have been like this. सारे ऐसे होते. It's also spin polarized current, and when they are interacting with the free magnetic layer, यहाँ की मान लो इस डायरेक्शन पे है, तो इन दोनों में एक टॉर्क एग्जिस्ट करेगा. It will try to move in this direction, to try to move in this direction. So this creates a torque. Now torque और जो spin transfer जो torque है, this is used, this phenomena is used to write. Okay, because we are involved in flipping. Spin flip, it involves spin flip. That means already is existing state है, उसके ऊपर we are imposing some different spin flips which were not there, and these spin flips are creating a set of bytes 0 and 1. तो क्या बोलते हैं, we are writing it. When we are writing it, we are using this spin transfer torque. It is a destructive process. But when we are reading it, if we read कर रहे हैं, already what is there, then we don't require this. We need to only know what is the resistance, what is the TMR. ऑलरेडी जो प्रेजेंट है उसका अगर हम TMR निकालें तो दैट इज इक्विवेलेंट टू रीडिंग इट. बट टू राइट इट वी नीड टू चेंज द रेजिस्टेंस. फॉर दैट वी रिक्वायर स्पिन ट्रांसफर टॉर्क. ठीक है यार, इज इट स्लाइटली क्लियर? मैं सिंपल तरीके से एक्सप्लेन करता हूँ. देयर आर 3 layers. One is a ferromagnetic layer which is spin. Means there is a certain magnetization direction. There is an in-between insulating layer which is say magnesium oxide. And there is another ferromagnetic layer which is free, which has got any किसी भी डायरेक्शन पे मान लो उसका ऐसा भी है, ऐसा भी, any direction, nothing is fixed, can move in any direction.
डायरेक्शन
मैग्नेटाइजेशन का M, मैग्नेटाइजेशन, सैचुरेशन मैग्नेटाइजेशन MS स्पेसिफिकली तुम अगर बोलो.
मैग्नेटाइजेशन और मैग्नेटिक फील्ड डिफर कैसे करते हैं?
क्या है? ससेप्टिबिलिटी. The magnetic field हो गई. What is M? Magnetization. What is H? Magnetic field. Negative for diamagnetic, but less than, much less than 1, 0 say, not common. If it is exactly equal to -1, then it is called perfectly diamagnetic, superconductor. And if it is positive and close to 1, then it is called a ferromagnet. मैग्नेटिक डोमेन्स कितना ओरिएंट हो रहे हैं मैग्नेटिक फील्ड के अकॉर्डिंगली. तो इस केस में मैं फिर बोल रहा हूँ दिस इज व्हाट इज कॉल्ड एंड 1T 1MTG system. One transistor, one LDG system. This is called an axis transistor. And this is called a magnetic junction. To do this basically stores. This is for storage के लिए use होता है. And this is basically for the flow of current के लिए. So our role is to read and write. So the writing and reading, both of them will occur in terms of bytes, 0 and 1. Okay. 0 is where the resistance are parallel. 1 is where the resistance are anti-parallel. Oh, I mean the resistance there. Okay. The spins are anti-parallel. So for reading you require TMR. Based upon that TMR, you can find out what is the resistance state, what is the reading state, and for writing you require STT. Writing के लिए तुमको STT चाहिए होता है because with the help of STT you are making the 0 and 1 change. ठीक है. अच्छा, यहाँ पे हम लोग मैग्नीशियम ऑक्साइड इंसुलेटिंग लेयर यूज करते हैं because it has got a crystalline property. इसका जो क्रिस्टल सिमेट्री है that acts as a very good filter to the spin current. Filter मतलब जो मान लो those which are anti-parallel it will not allow it to pass through. Those which are parallel it allows it to pass through. This is an LTJ system. Okay. Now, for every current or this to be working और ये जो spin transfer जो torque है, इसके लिए एक critical current density होती है. Correspondingly, it has a critical current. When it starts to flip, automatically the flip होना शुरू नहीं होगा. We have to give a certain current. मान लो the dimension of the system is 80 nanometer. 80 nanometer into 80 nanometer. इसका एरिया है, cross-sectional एरिया. वहाँ से करंट जा रहा है. This cross-sectional एरिया. और मान लो JC है 2 into 10 to the power -6 ampere per centimeter square. इसका क्रिटिकल करंट कितना होगा फिर? क्रिटिकल करंट एरिया कितना होना चाहिए? फाइंड आउट. 25? Maybe. It should be 2 into 64, 128. इसका यूनिट कितना होगा? Something. Unit and power, something to do with power or unit. That is important.
10 to the power minus 10 is exercise.
Unit? Unit?
Ampere centimeter.
No,
हम
it's
एक्स्ट्रा में
0.128 milliamperes. Take the next one. 0.128 milliamperes is the critical current. मतलब इस करंट से हमारा सिस्टम राइट करना शुरू करेगा. अच्छा, नाउ मैं बोलता हूँ कि इफ आई say that I would like to have my critical current as 0.5 milliamperes. ठीक है? हाँ. So question is whether it is feasible. Feasible होगा. अगर करंट बढ़ा देता हूँ तो क्या क्या प्रॉब्लम हो सकता है? इंक्रीज द करंट, नॉर्मल क्या होता है? इंक्रीज द करंट, किसी भी जगह से मैं अगर करंट बढ़ा देता हूँ तो व्हाट इज द थिंग दैट यू फर्स्ट ऑब्जर्व अपार्ट फ्रॉम हीट जनरेट होता है. E is equal to I square R T. This is the power generated. मान लो टाइम है 100 नैनोसेकंड्स और रेजिस्टेंस है 100 ohms. ठीक है? That is P. पावर कितना होगा? I square R T. In terms of watts बोलो. What? The is what? 2.5 over 2.5. It should be around नहीं. अच्छा, which current have you used? Unity. ये वाला current. हाँ, 2.5 microwatts. P is equal to 2.5 microwatts. ठीक है? And if
Sir, 2.5 into 10 power minus 12 watts आता है.
अच्छा, स्विचिंग टाइम मैंने 10 नैनोसेकंड दिया था ना, से इसको 10 नैनोसेकंड बहुत ज़्यादा हो गया. 10 नैनोसेकंड. अब देखो कितना आ रहा है. 1 डिग्री कम हो जाएगा. 5 स्क्वायर और सब तो 10 है और तो कुछ प्रॉब्लम नहीं होना चाहिए. 5 स्क्वायर मतलब I स्क्वायर मतलब 2.5 to 25 milliampere square. I square मतलब 100 ohms, 100 into 10. This is 100 ohms and this is 10 amps. तो मिली मतलब 10 to the power 6 minus 6 यहाँ पे हो जाएगा, ये into 10 to the power 2 यहाँ पे हो जाएगा, into 10 to the power 100 to 10 to the power minus 100 minus 9. So that makes it to the power minus 4 to the power 0.5, so it's okay, so it will be 2.5. अच्छा, so now what is the value?
0.25 to the square over I square actually.
Yeah. अच्छा, now the question is what is the power per unit time? So then you have to multiply P again with T. ठीक है. Now the question is ये जो STT MTJ है, it has got a value of 0.121 picojoules per bit इसका power है. And we are getting the power as 0.25 picojoules. इसके साथ जो अगर हम टाइम को मल्टीप्लाई करें तो 0.25 क्या 0.25 picojoules. Right? Now this is within this range. But my question was whether this 0.5 milliampere was feasible or not. The answer is yes, it is feasible if you theoretically look. ये इस range में आ रहा है. But the question is whenever we are going to the nanoscale, so there are some localized heat generators. Localized heat generation. ठीक है. Localized heat generation. And how do we calculate the localized heat generation? We need to calculate localized heat generation by the temperature gradient dT by dx. So dT by dx in this case ये डिपेंड करता है पावर जनरेशन डिवाइडेड बाय K and A. P तुमको पता है कितना है पावर, एरिया भी तुमको पता है. What matters is the K. What is K? This is the thermal conductivity. This is the thermal conductivity. Watts per मीटर केल्विन. ये जो सिस्टम है फेरोमैग्नेट, फिर एक ऑक्साइड NgO, दूसरा एक फेरोमैग्नेट. इस सिस्टम का कोई एक के नहीं होता. एवरी सेक्शन हैज गॉट इट्स ओन के. इसमें सबसे जो डिसाइडिंग फैक्टर है इज दिस इंसुलेटिंग लेयर. And it has got 5 watts पर मीटर केल्विन, ये इसका थर्मल कंडक्टिविटी इज एक्चुअली लो, इट कैन नॉट कम बैक ड्यू टू इट्स लोअर. इन सब के हाई है, दे आर मेटल्स के यूजुअली हाई होते हैं, मेटल्स और एलॉयज के. लेकिन ये जो कनेक्टिंग पॉइंट्स है जो कि कॉपर और टैंटलम से बना हुआ है, लेकिन दिस इज द हेड. इससे क्या होता है कि हीट जनरेशन होता है. हीट जनरेशन होने से इफ यू रिपीटेडली use an MTJ for writing. Reading तक ठीक है, because we are not using any spin transfer torque. But if you use MTJ for writing, then actually the heat actually damages. Heat is a deciding factor. So we need to remove the heat. System we need to remove the heat. To remove heat करने के there are different ways by which we can remove heat. First is if you lower the critical current. ठीक है. Second is if you lower the dimension. Dimension means if you lower the area. Third is if you use materials which has got high polarization. Fourth है if you use, instead of giving the current continuously, if you use pulses. Ten to 50 nanosecond pulses you use करो. So these are the factors by which you can reduce the heat. लेकिन these are all temporary factors. They are not long standing. Current को अगर तुम कम कर दोगे, if you lower the current, so it may so happen that कि room temperature पे जितना heat generate हो रहा है, that is enough to erase your जो तुमने लिखा है, memory erase कर देगा. So you need to have certain level of current to keep the memory intact. अच्छा, पोलराइजेशन हाई न्यूट्रल यूज कर सकते हो. दो न्यूट्रल जिसका P तो हाई है, जैसे कि हॉस्टल अलॉयज, एरिया डायमेंशन कम होने का मतलब क्या है? इसका मतलब है कि जो मैग्नेटिक मटेरियल है, मैग्नेटिक मटेरियल का वॉल्यूम चेंज करना, इसका जो वॉल्यूम फ्रैक्शन है उसको घटा दें. सो द लेस द मैग्नेटिक मटेरियल इज, द लोअर करंट इज रिक्वायर्ड टू स्पिन फ्लेम. और करंट पल्सेस एक साथ करंट रिक्वायर्ड पल्सेस बिकॉज इट गिव्स इट सम थर्मल रिलैक्सेशन. हीट जो जनरेट हो रहा है, इट कैन relax by means of thermal relaxation. It gives some amount of time, so time मिल जाता है. So these are all temporary. इसका जो real solution है is we switch to a new way of writing memory that is called SOT. From STT we are moving to SOT. SOT का मतलब है spin orbit tunneling. Spin orbit tunneling. ठीक है. अच्छा, spin orbit tunneling को सब तो I think you know what is the spin orbit effect. Spin orbit coupling तुम लोग जानते हो. What is this spin orbit tunneling? इसको जानने के लिए you need to understand something called Magnus effect. क्रिकेट में जब बॉल हम छोड़ते हैं ऐसे ना, ऐसे साथ if you associate a spin to it, it changes its trajectory. ठीक है, मतलब यहाँ से ये एक स्टम्प है, यहाँ पे एक स्टम्प है. On the first case में it is going like this. Case 1, and there is no spin associated with it. लेकिन if you इसके साथ एक spin associate कर देते हो, तो मान लो ये ऐसे जाके ऐसे घूम रहा है. Turn जो हो रहा है, this is called magnetic effect. The same thing happens here. हम लोग क्या करते हैं कि इंस्टेड ऑफ प्रोवाइडिंग द करंट वर्टिकली, हम लोग नीचे से एक करंट पास करते हैं which is consisting of electrons. यहाँ पे इलेक्ट्रॉन्स रहता है और इसके ऊपर यू हैव द मैग्नेटिक फील्ड, सॉरी मैग्नेटिक मटेरियल. यहाँ पे जैसे स्पिन इज कॉजिंग इट टू मूव बैक, उसी तरह से द स्पिन ऑफ द इलेक्ट्रॉन्स हियर दे कॉज टू फ्लिप द मैग्नेटाइजेशन इन द मैग्नेटिक मटेरियल. ठीक है. And spin orbit turning is usually observed in materials like heavy metals, in topological insulators, in 2D materials. Normal silicon में cannot take this. Why we are using heavy metals? Because यहाँ पे जो electric field is very strong. The electron is in the effect of electric field. So due to very high number of protons और एक nucleus का जो combination है, it leads to very high electric field. This is the reason. Topological insulators क्या है? Those insulators which are insulators in the bulk. Topological insulators. किस चीज को बोलते हैं? Topological insulators which are insulating in the bulk. Bulk में they are insulators, लेकिन at the surface they are conductors. ठीक है. A 2D material तुम लोग जानते हो, graphene, any which has got such dimensioning. So what is the advantage of these materials? इसमें क्या होता है कि ये why are these two advantageous compared to this heavy metals? Heavy metals में क्या होता है कि if I have certain number of electrons, so there is some chance that all of them will not have the spin in the required direction. लेकिन topological insulators and 2D materials में all the electrons that are following, they have a certain direction of spin because there is nothing below कुछ नहीं. 2D materials में तो है ही नहीं और topological insulators में this is an insulator. That is why they are advantageous. So this actually removes the problem of heat loss associated with STT and Mram. ठीक है.